Earth is doomed. That's the word from scientists who study the lives of the stars. When our sun becomes a senior citizen, it will balloon to many times its current size and vaporize our atmosphere. It might even swallow the Earth whole before it shrinks and fades away. The good news is that we won't be around when all this happens. The sun won't expand for another 5 billion years. The even better news is that the sun's death throes will help create another generation of stars. This is a story about renewal, about how old stars breathe new life into the galaxy. A star-filled night, majestic and serene. Surveying the heavens, we can be forgiven if we think that the stars will last forever. But the apparent constancy of the stars is nature's grandest illusion. If we could watch for millions of years, we'd see stars being born, going through middle age, and dying. A scan of the night sky reveals stars of all ages. For example, the constellation Lyra is emblazoned with blue-white Vega, one of the energetic youngsters of the galaxy. In the constellation Scorpius, the reddish star Antares is a cool star in its declining years. Stars are born in nebulas with evocative names like Lagoon, Trifid, and Eagle. Utilizing the superior vision of the Hubble Space Telescope in orbit high above the Earth's atmosphere, astronomers have peeked inside these shrouds of gas to witness baby suns flickering to life. They've also examined nebulas with names like the Helix, the Ring, and the Eskimo. These celestial smoke rings are the last gasps of dying stars. Astronomers have even studied the skeletal remains of stars that died violently in blinding explosions thousands of years ago. These snapshots of the life cycle of the stars have given us a new appreciation of life itself. Every living thing on Earth is based on the endlessly adaptable chemistry of carbon atoms. But there wouldn't be a single atom of carbon in the whole galaxy if the stars weren't evolving.
Long ago, the ancient people thought that you could change worthless elements into more valuable ones. The alchemists thought that you could turn tin and lead into things like silver and gold. And we now know that doesn't happen, at least not here on Earth, but it does happen in the stars. This alchemy of the heavens has manufactured the elements that we are now made of. The carbon that life is based on, the nitrogen that fills the air, the oxygen we breathe, the iron in our blood, calcium in our bones, were all created by stars in one way or another. And the story of how those elements were created is really a very fascinating one.
A good place to start is with an ordinary star like our sun. The sun is a sphere of hot hydrogen that's in a battle with the force of gravity. Gravity tries to collapse this massive bulk, but the sun fights back by releasing energy from its nuclear furnace.
The sun is actually a very well-balanced nuclear reactor. It produces energy for literally billions of years by fusing hydrogen into helium. And it's been doing this now for about 4.5 billion years and remaining virtually stable. One thing that's changing in the sun is its chemical composition, not the outer layers that we see. But in the core of the sun, the hydrogen is gradually being changed into helium And when it runs out of hydrogen completely, that's when the real changes will occur. That's when the sun is going to swell up and become a red giant.
The last-minute growth spurt occurs when the aging sun ignites its stockpile of helium. In response to the sunburst of energy, the sun balloons into a vast, pulsating, red giant star. But the fuel-hungry behemoth is teetering on the brink of collapse. Its nuclear furnace manufactures successively heavier elements in a desperate bid to stay lit. The star has only a tenuous hold on its distended atmosphere, yet gravity threatens to crush its core. Finally, the central fire goes out. The inner regions begin cooling off, and the rest simply floats away. If our observations of other stars are any indication, the sun will slough off layer after layer of gas to form a gleaming cosmic ring called a planetary nebula. The label is a misnomer, for these huge but insubstantial objects have nothing to do with planets. 18th century astronomer William Herschel thought the aqua-colored disks looked like ghostly planets. He began calling them planetary nebulas, and the name stuck.
Now, a planetary nebula represents the final stage in the evolution of a star like the Sun. So we think that about 5 billion years from now, the Sun will gradually begin to exhaust its nuclear fuel. It will initially expand out to a red giant star, maybe 50 or 100 times its present diameter, and then those outer layers will be lost into space, leaving only the hot core of the Sun at the center. So the hot core will send out ultraviolet radiation into the surrounding gas, making it glow and become visible as a nebula, like the Ring Nebula. So then that nebula will gradually dissipate away into space. Then the remnant core will gradually fade away and become what's called a white dwarf star. So you can ask, what's going to become of the Earth? You know, the poet said, will the Earth end in ice or fire? What's going to happen is we'll get the fire first and then the ice. First as the red giant burns the Earth to a cinder, and then whatever is left will freeze solid as the sun becomes a white dwarf and fades away.
Of course, we can't be completely certain about this. A minority of astronomers take an even more pessimistic view of the far future. They believe the sun will grow so large it will engulf the Earth completely. In this scenario, our planet would spiral into the sun's interior and be vaporized sometime before it hit the core. The sun, on the other hand, will end not with a bang, but a whimper. It will not erupt in a fiery supernova explosion the way more massive stars do. Supernovas blast their contents into space, thus providing the raw materials needed to build new stars and planets. When our sun produces a planetary nebula, it too will disperse its elements. However, the transition will be more gentle.
The planetary nebulae make an important contribution, especially when it comes to nitrogen. Most of the nitrogen on Earth came from stars that did not explode, stars that instead shed their atmospheres as planetary nebulae. And to be perfectly honest, I think the greatest contribution the Hubble Space Telescope has made concerning planetary nebulae is just the beautiful photographs.
Hubble's gallery of planetary nebulas is full of intricate and colorful subjects with evocative names like spirograph, twin jet, the ant, and a favorite of backyard skywatchers, the Cat's Eye Nebula. Winking at us from 3,000 light years away, the Cat's Eye displays a complex yet remarkably symmetrical swirl of multicolored gases. Photos like this one by the Hubble telescope have forced astronomers to rethink their ideas of how planetary nebulas form.
Well, you could think of a lawn sprinkler as it rotates around and throwing out material in different directions. So we think there's a precession going on, a wobbling of the star as it ejects material in different directions. Now, why it would do that is still a bit of a mystery. It may involve magnetic fields or very possibly the action of a companion star or maybe even a companion planet. More generally, we're finding that almost all planetary nebulae are not round, as we used to think, but have an elongated structure. Even the famous Ring Nebula, which at first glance looks like it's round, we think is probably a cylinder or a barrel structure seen down its axis. So it's only from our point of view that it looks round, and from a different point of view, it might well look like a quite elongated structure.
The Helix Nebula, 450 light-years away, is the closest planetary nebula to Earth. Anchoring the helix is a shriveled white dwarf star whose outer layers dispersed about 10,000 years ago. The Space Telescope has looked inside the helix and discovered hundreds of tiny, dark blobs of gas, or at least they look tiny.
In the famous Helix photograph, you see streams of material then being blown off of these dense knots of material, forming what looks like a comet, although it's a comet on a vastly larger scale than in our own solar system. In fact, those blobs are already several times the size of our entire solar system.
Gigantic nebulas, an incredibly diverse population of stars, countless planets. These astral wonders are all part of a city of stars called the Milky Way galaxy. Like a real city, it changes over time. And there's a lot more action in the galactic city than meets the eye. Our Milky Way galaxy is immense. A rocket traveling at the speed of light, the galactic speed limit, would take about 1,000 centuries to cross it. A few 100 billion stars live here. Our sun and its retinue of planets reside in a suburb far from the center of town. It's a sprawling, uncongested neighborhood, typical of the galaxy's outer regions. The stars here display a wide range of mass, brightness, and color. Stellar nurseries and graveyards dot the star scheme, or at least we think so. It's the astronomer's job to piece together these various elements into a coherent whole. To that end, an international collaboration of radio astronomers is conducting a project called the Galactic Plane Survey. The project members are pooling their data to chart the band of the Milky Way in more detail than ever before. The survey began modestly in the mid-1990s at the National Research Council Radio Observatory near Penticton, British Columbia. This aperture synthesis telescope comprises several radio dishes linked electronically so that the instruments operate like one huge antenna. The synthesis telescope scans the Milky Way at the radio frequency emitted by hydrogen atoms, the galaxy's most abundant element. The constellation Cygnus is a rich tapestry of stars and hydrogen gas clouds, which shine red in this optical image, but mapped at the radio wavelength of the Galactic Plane Survey, and with a little help from satellite surveys, objects materialize that are difficult or impossible to see at optical wavelengths. This region of the Milky Way is being energized by the creation and destruction of massive stars. The remains of several stellar explosions are visible. Compact nebulas reveal the presence of a newly formed hot star embedded in a dense shroud of heated gas. Stellar winds from other young stars, and possibly from previous explosions, have blown clouds of gas and dust into long, curving filaments. All this gas and dust forms what astronomers call the interstellar medium. The content of the medium is mostly hydrogen and is incredibly tenuous. Its temperature is typically more than 240 degrees Celsius below zero. In some places, the interstellar medium gravitates into dense molecular clouds, regions where the gas and dust is clumping together. It's here that stars are made. Astronomers are anxious to study the molecular clouds, but peering inside this murky stuff requires help from radio telescopes.
The reason we look in the radio is that these very dense regions, although they're mostly composed of gas, there's about 1% of the total mass in the region is very, very fine dust grains. And those fine dust grains will intercept optical light coming through and scatter it and absorb it. And so if you look at one of these regions on the sky with an optical telescope, what you usually see, you see a field of stars around the region that's going to form, and then the region where all the action is going on is black. You just can't see into it. It just looks like a blank region of space. Whereas when you go into the radio wavelengths, you see the opposite effect.
Radio waves can penetrate these dusty regions, so radio telescopes can record their hidden features. The frigid clouds are strong radio emitters, so their structure can be probed in considerable detail with radio antennas. The incubating star systems inside the clouds also shine at radio wavelengths.
If you think about it, basically what happens is that the difference between a star and the interstellar medium is that a star is very dense. And so to form a star, you have to take, say, an amount of mass that's the same as our sun, which might be spread out over, say, 3 to 5 light years in diameter, and compress it into something that gets small enough and hot enough eventually to form a star. It turns out that the regions that get dense are also the regions that are cold. They do eventually heat up when the star turns on, but in the early collapse phases, as the material is raining down into the center, they stay cold and dense and cold and dense. Basically, they're very efficient at cooling, at radiating away the energy that's formed because of all the molecules that form in the dense regions.
The theory behind star formation is straightforward. A clump of hydrogen gas collapses under the force of gravity until it gets so small and so hot, nuclear reactions are triggered and the new star begins to shine. This incredible shrinking clump can't get too hot too fast, though, or else it will stop contracting. To condense into a star, the object must get rid of its excess heat energy. The theory suggests that a number of molecules, primarily water, perform this function. But the theory might be in trouble, according to an Earth-orbiting radio telescope called SWAS. The acronym stands for Submillimeter Wave Astronomy Satellite.
SWAS was designed primarily to look for a few specific molecules in star-forming regions that are very key to understanding how the process of star formation works. And one of these is water, and the other is molecular oxygen.
Those water molecules would emit radio waves that could be picked up by the spacecraft's antennas. More importantly, the radio waves would remove energy from the nebula, serving to keep it cool. If it contains enough water, an interstellar cloud will stay cool enough for long enough to collapse into a cluster of stars. So, the SWAS team went looking for water in space. They found both good news and bad.
What we did find was that water is everywhere. It's all over in the galaxy. We've looked at many, many different regions, but it's far less abundant than we had ever expected. It's about 100 to 1,000 times less abundant than we had predicted through these chemical models.
SWAS also looked for oxygen. Oxygen molecules, like water molecules, would help cool the nebula during its formative stages. More than this, oxygen is a vital component for so many things we know and love, like rocks, soil, air, us. It only made sense to look for oxygen in regions where stars and planets were forming.
In the rest of the galaxy, it seems like there's far less oxygen than there is in the solar system. It's underabundant by a factor of about 3. So the thought was, is our solar system a strange place? Do we have more oxygen than there is elsewhere in the galaxy? Or is the oxygen simply hiding in some form that we were previously unable to detect?
The oxygen SWAS was looking for is called atomic oxygen. In terms of chemical structure, it's just a bunch of individual oxygen atoms. But perhaps oxygen atoms in space are doubling up, as they have a tendency to do. Cosmic oxygen could be hiding in the form of diatomic or molecular oxygen, which is the kind we breathe here on Earth.
What we've done with SWAS then, after we built it and launched it, is we've looked at all of these different regions, and we have not been able to find molecular oxygen absolutely anywhere after hundreds of hours of pointed observations in one particular area of the sky, where the signal, the noise levels are down to levels that are sort of unprecedented in radio astronomy. We're not able to find that oxygen molecule anywhere. So the question is still, is the Earth an oddball? And there really isn't that much oxygen in the rest of the galaxy. Or is the oxygen hiding in yet another place that we don't know, another form of oxygen that we haven't been able to detect? So we still have to, it's a puzzle for us that we still have to solve.
Since that interview, the SWAS team has found a few star systems where water seems to be plentiful. It's a complete mystery why there's a wide range in water contents among different star systems, or indeed why there's any variation at all. Oxygen, hydrogen, carbon, iron, nitrogen. The interstellar medium contains these and other elements in varying amounts. They all come from the interiors of stars, and they will all go into the making of new stars. How does this galactic recycling machine work? The answer lies with nature's most spectacular fireworks, a supernova explosion. It may be that our sun will simply fade away when it gets old, but bigger stars go out with a bang, literally. The stellar heavyweights of the Milky Way die in a blinding flash called a supernova. These stars consume their hydrogen in only a few million years. Then gravity takes over and the stars begin to shrink. This triggers other sources of fuel like helium and carbon, and the star rebounds as a red giant. But when even these reserves are depleted, the internal heat source shuts down and suddenly there's no pressure to hold up the star. The core starts collapsing and the star's outer layers fall on top of it. In a matter of seconds, the core has become so dense, it's as though the infalling material has hit a brick wall. It bounces off in a shock wave that propagates back outwards through the star. Once the wave of energy reaches the surface of the star, the cosmic fireworks burst into view. The supernova becomes brighter than the combined light of all the stars in its own galaxy. We know this from observation of supernovas in remote galaxies millions of light years away. During a supernova explosion, a star's core is crushed by gravity into an incredibly dense ball called a neutron star. Neutrons are subatomic particles that, together with protons, make up the nucleus of an atom. A neutron star has been crushed into such a compact volume that all the subatomic particles have coalesced into neutrons. Gravity has shrunk the star to the smallest possible size by turning it into a gargantuan atomic nucleus.
It's incredibly dense, so this is something like 1.5 times the mass of the sun crunched into the size of a small city, something like a radius of 10 kilometers. That's our best estimates. So very dense. So 1 teaspoonful of neutron star material weighs several tons. And if that's not weird enough, these things rotate very, very rapidly. So the typical neutron star will rotate a few times a second, but the fastest ones, or the fastest one we know of, rotates over 600 times a second. So something, incredible density rotating as fast as your household blender.
Some neutron stars seem to have bright patches on their surfaces. The star's rotation brings these hot spots in and out of our view many times each second. This makes the star seem to flicker or pulsate like enormously speeded up lighthouses. So we call these neutron stars pulsars. The youngest and most studied pulsar discovered so far is enveloped in a roiling cloud of debris called the Crab Nebula. The Crab is, for good reason, the most famous supernova remnant in the heavens. The Crab pulsar flashes at us with machine gun-like regularity, 30 times every second. It's as though the brightest supernova remnant in the sky is winking at us, trying to get our attention. In fact, it's received plenty of attention going back a long time. Nearly 1,000 years ago, astronomers of the Chinese Imperial Court recorded what they called a guest star in the constellation Taurus. It was the year 1054 in the Western calendar, and the supernova was so bright it could be seen in broad daylight for 3 weeks. It was nearly a year before the guest star faded from the night sky. Centuries later, astronomers size up the wreckage through their telescopes. They have learned that the Crab is expanding at more than 1,500 kilometers per second and is thousands of times larger than our solar system.
The Crab, although it's quite far away by earthly standards, 6,500 light years or so, it is so far away, but it is moving so rapidly that over time we can actually see the material change, especially when using the spatial resolution of the Hubble telescope. So when we come back and look at it at different times, we actually can see how things have moved and changed as a function of time.
They've been looking at the Crab periodically with Hubble, and you can go zoom right into the central region and you can see the pulsar, but you can also see all the interactions around it. And they've turned a series of frames into a Hubble movie. With the Crab Nebula, things are changing so fast that you can see things evolving over the course of just weeks and months. And you can see like a wind, a concentric, it's kind of like throwing a rock into a pond and you get concentric ripples moving outward. It's the same with the Crab Nebula. You can see that the pulsar, which is spinning 30 times a second, is giving off this wind that's just radiating outward from the center and interacting with all the interstellar material surrounding the pulsar.
As we take that a step out from this diffuse nebula, the synchrotron gas around the pulsar, we see that gas interacting with the ejecta from the explosion, the filaments we call them, the brightly colored things in the Hubble picture of the Crab. That material is literally star stuff. It is the surface and interior layers of that star that have been thrown out back into interstellar space and ultimately will go out and presumably participate in a new round of star formation.
Not all of the galaxy's heavyweights end up as neutron stars. The most massive stars meet an even stranger fate. When an ultra-massive star goes supernova, its outer layers blow off in the way we've seen, but the core collapses totally. The nuclear forces that hold neutron stars together aren't strong enough to overcome the suddenly magnified gravitational field. So, the whole core goes down the cosmic drain. It shrinks to a point and vanishes, tearing a hole in the fabric of space-time and leaving only its gravitational field behind. Like the smile of the Cheshire Cat, what had been a giant star has become a black hole. Black holes are, by their nature, tough to spot. But there is a way we can detect them indirectly. If a black hole is a member of a binary star system, it will pull gas from its neighbor. The material gathers into a whirlpool around the black hole, then spirals down the drain. As the particles get closer, they swirl faster and faster, heating up until they glow with X-ray radiation. The X-rays can be detected by orbiting X-ray observatories.
The material that's hot that we see near the black hole is emitting its last cry of radiation. It's right near the black hole and soon will be lost to the universe forever. As material falls into the black hole, it can no longer emit any kind of radiation that could ever be detected because the gravity from the black hole is so strong that the light, even from a very, very hot gas or any very hot atoms or molecules that have fallen into the black hole, can never leave. There's no way that we can ever detect anything that has already fallen into the black hole. In other words, the information, any information about that material is lost to us. And although the material is certainly still in the universe, there's no way for us to interact with it at all. And so for all practical purposes, it's gone.
Not even the largest stars go cleanly into gravitational collapse. The birth of a black hole is a messy process, and it spills into space material that gets incorporated into a new generation of suns. Our sector of the Milky Way is certainly well stocked with recycled star stuff. The sun is a prime example, and so are the planets. For that matter, so are we. Yet, as we'll see, the process of star formation is not a simple one, and the results aren't guaranteed. Outer space is full of clues to the way that stars are born, and some of them are easy to spot. In some parts of the galaxy, the interstellar medium glows in the dark. If it gets energized in the right way, a cloud of hydrogen will light up and shine with a distinctive reddish color. A typical example is the Lagoon Nebula in the constellation Sagittarius. The lagoon is energized by the ultraviolet radiation from dozens of hot young stars embedded within it. This swarm of sibling stars is evidence that the lagoon is more than just a pretty picture. It's a hotbed of star formation. Astronomers know that prenatal suns are still incubating deep inside the lagoon. They have also learned that sometimes the miracle of birth comes with nasty complications. The bizarre environments that harbor new stars can be seen in the constellation Orion. Orion's distinctive shape is well known to sky watchers. His belt of 3 bright stars is easily visible to the naked eye. Dimmer stars point the way to the famous Orion Nebula, a favorite target for backyard astronomers. And no wonder, here lies one of the most remarkable star-forming regions in the heavens. The Hubble telescope effectively has zoomed right inside the Orion Nebula. In addition to the energetic young stars that are causing the nebula to glow, Hubble has revealed fledgling protostars shrouded in dusty cocoons. Scientists wonder if stars and planets will emerge from this web of dust and gas. Canadian astronomer Doug Johnstone has scrutinized the Hubble images, looking for faint clues of stellar genesis.
What we're finding in the Orion Nebula is quite intriguing. Not only are we looking at one of the nearest regions of star formation, but this is the closest region where young stars are forming of all masses. So high mass stars as well as low mass stars. And this is unique in the sense that the high mass stars that are there are putting out so much energy that they're actually affecting the environments of the younger stars. If you look at a beautiful picture of the trapezium region, what you'll see is 4 stars in a trapezium-like configuration down in the middle of a nebula of glowing gas. That nebula that you're looking at is hot gas heated by those 4 stars. Those 4 stars are putting out a lot of energy and heating all of the material around them. You know, who's ever heard of stars with tails? And yet if you look right in around the trapezium, you see these little objects that look just like comets. What's really happening is that you have young stars, and those young stars have disks of material around them. And those disks of material are being heated by those high mass stars. And as the material comes off of the disk, it comes out into the environment. It starts to glow, like a comet does, but then the wind from the high mass star blows that material back into what looks like a cometary tail. The size scale is exactly the same size scale as the solar system, giving more credence to the notion that the disks which we know we observe around stars are the same size as our solar system and are the link between star formation process and the planet formation process.
But Johnstone and his colleagues aren't so sure that planets will form in these dusty disks every time. The big stars nearby make life difficult for the next generation of infant stars trying to grow. And if the stars can't grow, there's no chance for planets.
So inside the disks, it's not entirely clear we'll ever get to planets in a region as violent, in a region as dangerous as the Orion Nebula, because what's actually happening are the disks are being destroyed on very, very short timescales. Less than 1 million years. Sounds like a long time to you and me, but 1 million years is a very, very short time in the life of a star.
The precarious nature of star birth is not restricted to Orion. On the opposite side of the sky, in the constellation Serpens, lies a massive star-forming region called the Eagle Nebula. Inside the Eagle are gigantic pillars of cool, dense molecular material, bordering a cavity of hot gas. Intense radiation emanating from the Eagle's blazing young stars is striking these cool pillars and eroding them, the way a powerful wind scours a desert. When Arizona astronomer Jeff Hester began analyzing these Hubble images, he noticed something else.
Buried inside of some of these things we found were stars. And we realized that in fact what we were seeing were the nucleus of star formation, star-forming cores of gas that were being uncovered as the material around them was evaporated away.
Hester thinks that as their protective envelope gets eaten away, the protostars become exposed to a harsh wind of ultraviolet radiation from the massive suns born earlier. The gale of radiation threatens to blow away the vital gases these stellar embryos need to grow. It might even rob them of their chance to become stars at all. Apparently, in the Eagle's nest, not every hatchling survives.
And so the star is going about its business, accreting material, growing larger and larger and larger. And at an arbitrary place in that process, along comes the hatchet. That's all you get. And that's now the size that that star is going to be. It's not going to grow any larger because it doesn't have anything to grow from. And so we're seeing the process. We're seeing at least one of the processes that determines the sizes that these stars actually reach. And so both the Orion Nebula and the Eagle Nebula are in a sense showing us a smoking gun. And that smoking gun is the effect that young, hot, massive stars have on their environment and have on the formation of stars in the region around them.
It might not always work flawlessly, but the process of star formation seems to operate on an impressive scale throughout the Milky Way. Just as remarkably, the galaxy harbors at least one species of sentient creatures that is trying hard to unlock the secrets of the galaxy. Those creatures have come to realize that they have a connection to the stars deeper than any they could have imagined. If all our surveys and in-depth analysis of the Milky Way have taught us just one vital fact, it is that everything is connected to everything else. Our galaxy is a vast recycling machine. In its dying blaze of glory, a supernova explosion forges all those exotic elements you learned about in chemistry class. Supernova remnants such as the Crab Nebula are brimming with building blocks for new structures in the galactic city. The Crab is dumping its mix of hydrogen and higher elements into the interstellar medium. There, in the fullness of time, it will blend with other clouds of star stuff and new nebulas will be formed. Our sun, its family of planets, and of course our planet, were assembled inside a nebula, whose contents in turn can be traced to the wreckage of expired stars. Small wonder that astrophysicists who study mysterious disks of gas in the Orion Nebula admit to a lifelong fascination with the night sky.
I come at this as a physicist. I want to understand. That's why I said the first notion that intrigues me is how the material's coming off of these disks, right? That's a physics problem. But when I go up to my family cottage in northern Ontario and I lie down in the bottom of the canoe as I've done since I was a young child and I look up at the stars, I don't worry about the physics. I look at the beauty of it.
For other astronomers, the beauty is not so much visual as conceptual. The very fact that we can figure out a process like the birth of stars is a source of wonder in itself.
How are stars forming way on the other side of the galaxy? Based upon this information that comes at you across the vastness of space. You know, you can look at a star and you can tell what is that star made of? And that star is on the other side of the galaxy. I mean, I just find that incredibly fascinating that you could do that.
If scientists are correct about their ideas of the way stars produce and distribute the chemical elements, they have uncovered a remarkable connection between the Milky Way and us. Simply put, humans are recycled star stuff. We owe our very existence to the countless stars that came before us.
I think that one of the most fascinating things that we've learned in astronomy in recent decades is we've learned an enormous amount about our own connection with the universe, the fact that we're a product of that. That we start by looking out and we see spectacular things. We see distant quasars, we see the Eagle Nebula, we see galaxies. We learn about all of those things. But then in the end, we find ourselves looking back inward and gaining a new appreciation of who we are and where we came from and what our connection with all of that is. We know enough now to realize that when the universe was very young, that there was hydrogen, there was helium, trace amounts of lithium, and that's about all. But you and I aren't made out of hydrogen and helium and trace amounts of lithium. We're made out of carbon and nitrogen and oxygen and phosphorus, and we're sitting here on a planet that has an iron nickel core and silicates surrounding it. Where did all of this heavy stuff come from? All of these other elements? And the answer is that they were formed on the insides of stars. Stars get their energy by taking lighter elements and fusing them to form more massive elements. And this process continues. Well, what good does that do us because we're not on the inside of a star? Well, as stars near the ends of their lives, they eject that material. They blow it away in winds. They eject it in planetary nebulae. They go supernova. And so all of that really chemical pollution is what to call it. The chemical legacy of those stars is blasted back out into interstellar space. So that when our sun formed and our Earth formed, now you had all of these more massive elements around so that you could do chemically interesting things, like build life, for example. If you look around the room, look out the window, the atoms that make up everything that you see were once a part of a star. And in fact, they were formed inside of a star. And so you and I are part and parcel with this process. We're the end product, in fact, of the chemical evolution of the galaxy. This isn't something that's removed. It isn't something that's out there. It isn't something that's apart. It's something that is inextricably connected with our existence. And I think that's maybe the most fascinating thing about astronomy these days.